So now we are going to see the moment of inertia of a hollow cone. So here we are given with a hollow cone of mass m, radius r and height h, and we wish to calculate the moment of inertia of this hollow cone with respect to an axis which is passing through the center of the cone. From the last video, it is pretty clear that the moment of inertia of the cone with respect to the axis of rotation should be independent of the height of the cone. Why? Because the height of the cone is a dimension which is parallel to the axis of rotation. So, it is quite clear. Now, let's try to calculate the moment of inertia of this hollow cone. So, before proceeding with further calculation, let us try to understand how do we generate a hollow cone. So, let us assume that we are given with a disk as shown in this figure, and we assume that this disk is made up of extremely thin, infinitesimally small strips which are rings. So this is a particular strip, ring strip, this is another strip, this is another strip, this is another strip. So this disk is made up of extremely thin strips of rings, and these are infinite in number. Now what we do is we select a particular strip, let's say this one, and we put it to a particular height. Let us try to understand with the help of this particular figure. So first let us consider this blue ring. So what do? Is we take this blue ring and we lift it up to this particular height. Again we select another particular ring. Again we take it and lift it up to another particular height. So eventually we take each of these particular strips and we lift each of these particular strips to a definite height, and the height by which a particular strip is lifted has a linear function. So what do we get eventually is, if we lift each and every particular strip to a particular height so that the strip touches this particular line, so we are going to eventually generate a hollow cone from a disk. So now let's do the reverse thing. Let us assume that we are given with a hollow cone and this is our axis of rotation. Now what we do is we try to assume that this hollow cone is made up of extremely thin strips. And now what we do is we try to shrink the dimension which is parallel to the axis of rotation of this cone. That is, we try to shrink this hollow cone along the height of this cone. So what are we going to get? On doing this, we are going to generate a disk. So while calculating moment of inertia, it is pretty clear that we can always shrink the dimension which is parallel to the axis of rotation. So the moment of inertia of a hollow cone should be equal to the moment of inertia of a disk of same mass and radius. So we expect the moment of inertia of this hollow cone about this axis to be equal to mr square by 2. So we have found this in a much smarter way without doing any nasty calculations. So let's try to verify this result by following a standard general approach. So let's do that. So what we are going to do is, at a distance x from this point, we are going to consider an elemental ring of thickness dx. So what is going to be the mass of this particular elemental ring? Let's say that the mass of this elemental ring is dm. So we can clearly write dm would be equal to m by pi r root over r square plus h square. That is the surface area of this hollow cone times 2 pi r times dx, where r is the radius of this ring and dx is the thickness of this ring. So we can also see that we can calculate the value of r. So As this triangle and this bigger triangle is similar, we can write r by capital R as x by root over r square plus h square. So we can write r as xr by root over r square plus h square. So we can simplify dm as 2m by r times root over r square plus h square times xr by root over r square plus h square times dx. So r gets cancelled out, so we get dm as 2mx dx by root of by r square plus h square. So what is the moment of inertia of this elemental ring? The moment of inertia is going to be simply dm times r square. So let us substitute the values. So on substituting the values, we get it as 2m times r square plus h square times x cube r square by r square plus h square times dx. So what is going to be I? I is going to be simply integral of di, that is, let's write the constant terms first, 2m r square by r square plus h square whole square times integral of x cube dx, where the limits are x are from 0 to this particular length. So from 0 to this particular length is root over r square plus h square. So let us simplify this. This is simply 2m r square by r square plus h square whole square times, on simplifying this, we get it to be r square plus h square whole square by 4. So we can see that r square plus h square terms cancelled out. So what are we left out with? So we are left with simply mr square by 2. We can clearly see that this is the same result that we have already predicted regarding the moment of inertia of this particular hollow cone without doing any calculation at all. So you can clearly understand the strength of this concept, that we can shrink the dimension which is parallel to the axis of rotation.